So, very good morning and welcome back to the next series. And now we are going to have two sessions where I completely conduct the class, in which I'll be explaining certain concepts because they require continuous and detailed explanation, right? Following that, we have 4 sessions today with me, right? So now in the morning sessions, it will be only I who would kind of engage the class, though I would welcome participation from you in terms of answering questions, right? But in the afternoon, just after lunch, because just after lunch, I'm sure that you won't be as attentive as you are in the morning, and therefore we'll have some exercises again in pedagogy where you will help create certain exercises, certain tutorial problems, right, with the guidelines that I explained to you. Anyway, let's now embark upon a study of transforms. Now, what is a transform? A transform is a change of paradigm, right? A transform is a change of paradigm. What is meant by the word paradigm? How many of you have heard the word paradigm before? Yeah, some of you have heard the word. What? Give me an explanation of the word paradigm. Yes, Saurabh, would you like to? Yes.
Previously used to use non-stick and
Yes. Very nice. That's a very good example. So, Saurabh, that's a very good example. Saurabh says one very simple and yet very interesting example of change of paradigm is that in the in the so-called old days, I won't say good or bad, the teacher would use a long stick to point to the board, right? To point out certain things on the board. Today, you don't need to carry a long stick. Instead, you use a laser pointer, which serves the same purpose, isn't it? So it's a change of paradigm. You're fulfilling the same function, but with different tools. That's what we do in a transform. We fulfill the same function. We want to understand systems. We want to characterize systems. We want to describe input-output relationships, but we do it in a different setting, right? And we do it in a different setting because it has certain advantages. It doesn't mean that the transform domain is always at advantage, but it could at some occasions be of advantage, right? So that is what we will appreciate as we go along. So paradigm literally means world view. The way we see the world, that's called paradigm. And here, of course, our world is signals and systems. The way we see signals and systems is our paradigm, right? Now, in particular, we are going to discuss the Fourier transform. The Fourier transform is named after you can call him a mathematician, scientist, in those days, more than 2 to 3 centuries ago. I think his name was Jean-Baptiste, but anyway, I'll just say J.B. Fourier. Now, Fourier actually was studying, good morning, Fourier was studying the propagation of heat waves, propagation of thermal energy, right? And he noticed that if he wanted to solve the differential equations which related to the propagation, it would be easier to think of the solution as a combination of sinusoids. It would be easier to think of the solution as comprising of sine waves, because you could then think of it as having several components. And of course, you calculate the strength of each component. So, you see, in the way Fourier solved the heat equation or the equations that related to propagation of thermal energy, he found that the problem of finding the function which satisfied the differential equation could be reduced to the problem of finding certain coefficients. Right? Now, anyway, this is in general, what we mean by change of paradigm. Very often, instead of trying to look in the dark, right, we decide that we have some idea of the nature of the signals or the systems that we are dealing with, and therefore we use the knowledge that you could think of the signals and also the underlying system as working on a set of components. And if possible, we can analyze the effect on each of the components individually and then combine the overall effect to see what happens in the system. Right? So, this is what is meant by a change of paradigm. Instead of working without any a priori knowledge, without any prior understanding of what kind of solutions to expect and so on, we work with the acceptance that there is going to be a set of functions with respect to which we can express the solutions, and we express the result in terms of that set of functions by finding only the coefficients in the expansion. Now, in particular, why sinusoids? Let us understand this. Sinusoids. Why? So, there are so many possible functions that you could choose, but why sinusoids, right? Now, in fact, one answer to that question comes from our knowledge of how a lot of physical phenomena work. Now, as electrical engineers, we know that when you try and generate a waveform, a voltage waveform, if you are trying to generate electrical energy, what are you doing? You are converting, very often you convert mechanical energy into electrical energy by using Faraday's principles, isn't it? By using a generator. Now, in a generator, what happens? It's the coil that rotates and a time varying voltage is created across the coil. Is that right? And that time varying voltage is periodic. So, the desire to deal with periodic functions can be seen as beginning from there if you are dealing with the current forms of power supply that you are familiar with, isn't it? Similarly, a lot of phenomena in nature are periodic, if you look at it, not just electrical phenomena. Look at seasons, for example. They are at least pseudo-periodic. That means they are almost periodic, but with a few variations period to period, right? They are pseudo-periodics. The pseudo-periodic characteristic of a lot of physical phenomena inspires us to think of the smoothest possible periodic functions. What do we mean by the smoothest? Smoothest possible and self-replicating periodic functions, right? What do you mean by self-replicating? When you pass them through a linear shift invariant system, they remain as they are in form, but change in parameters. Right? We now appreciate this a little better. So, listen to what I am saying carefully. What is the beauty of sinusoids? When they pass through linear shift invariant systems, they remain the same in form, but change in parameters. Now, in fact, take the example of what is called phasor analysis. All of us are familiar with phasor analysis, right? Being in the domain of electrical or electronics engineering, all of us are familiar with phasor analysis. What is the principle of phasor analysis? Take a moment to reflect. The principle of phasor analysis is that in an RLC circuit, when a phasor is given as an input, what is a phasor? Actually, a phasor is not quite a sine wave. A phasor is one of the two components of a sine wave. We will come to that in a minute. But for the moment, let us assume that a sinusoidal input is given, right. So, when a sinusoidal voltage is applied of a particular frequency on the circuit, or a sinusoidal excitation, it could be a voltage, it could be a current source, whatever it is. What is the nature of the response all over the circuit? It is also sinusoidal of the same frequency. Now, this is not true, say for example, if you gave a triangular input. If you gave a triangular wave as the input to an RLC circuit, and if you observe the output at every point, the output would not be a triangular wave. But if you give a sinusoidal input, theoretically also the output is sinusoidal everywhere of the same frequency. So, what changes at different points? It's the phase and the amplitude. Is that right? So, this is what is meant by self-replicating. Yeah, phasor analysis. The essence is that sinusoids are self-replicating. When an RLC circuit is excited. Is that right? Now, of course, this holds for sinusoids, it does not hold for all functions, but it holds for functions in addition to sinusoids as well, which we shall see in a minute, right. Be that, what are we trying to do in Fourier analysis? We are therefore trying to look at signals and systems, thinking of signals as a combination of sinusoids, or rather that is the context of real signals. But if we are talking about signals in general, which could also include complex signals, then we will think of them as combinations of what are called phasors. Now, phasors are not quite the same as sinusoids. As I said, phasors are actually rotating complex numbers, right? And very often we wonder, why should we be dealing with complex numbers when there is no complex voltage or complex current anywhere really in the circuit? This is something which all of you should reflect carefully on, not just for a course on signals and systems. But in electrical engineering, very often the young beginner student could always be curious why we should be bringing in complex numbers when there is no real complex voltage or complex current, right. I would like you to think for a little while before I take up the answer to this question. Why should we be dealing with complex numbers? But I would like you to think of the answer I am going to ask you after a little while. But before we come to that question, so in fact sinusoids have two complex numbers rotating in them. Sinusoids are formed by two oppositely rotating complex numbers. But the question is, why should we be thinking of sinusoids that way? Why can't we instead deal with the sinusoid directly? Right? That's the question that we need also to address and answer. Anyway, coming to, the beauty of sinusoids. Now, what is so beautiful about sinusoids? Sinusoids are self-replicating under all these operations. Linear combination, differentiation, integration. So, if I take two sinusoids of the same frequency, now I am talking about sinusoids unifrequencies. I should qualify this by saying unifrequency sinusoids. Unifrequency means a single angular frequency, right? So, unifrequency sinusoids are self-replicating. That means they retain their form under the three operations mentioned here. When I take a linear combination of two sinusoids of the same frequency, let us write that down, you get another sinusoid of the same frequency. So, you have, for example, A1 cos omega naught t plus phi 1, sorry, plus A2 cos omega naught t plus phi 2 can be rewritten as A3 cos omega naught t plus phi 3. And we all know how to find A3 and phi 3 in terms of A1, phi 1, A2 and phi 2, right. We can easily do it using simple trigonometry. We expand this and then expand this and compare the coefficients of cos omega naught t and sin omega naught t, right. So, one can easily find out A3 cos. Therefore, this is the self-replicating property under linear combination. If you differentiate a sine wave of a particular frequency, it results in a sinusoid of the same frequency, right. The amplitude changes and so does the phase, right. Similarly, if you integrate a sinusoid of a particular frequency, so I am talking about the indefinite integral, it remains a sinusoid of the same frequency, and of course, again the amplitude and so phase also change, right. What is the change of phase when you differentiate or integrate? How much is the change of phase? 90 degrees, that's right. So, when you integrate or differentiate, the change of phase is 90 degrees, is that right? Now, you see, let us look back at our linear shift invariant system that we were talking about yesterday. Now, we talked about the operation that connects the output to the input. So, yesterday we looked at a discrete system, discrete linear shift invariant system. And we looked at the input-output relationship. We said the output y of n is equal to summation k going from minus to plus infinity. Well, the way we wrote it is xk hn minus k. Okay, so here hn was the impulse response. Now, you can also look at the same operation or the same relationship in a different light. We could think of x and h, both of them are sequences, right. X is a sequence, that means a discrete signal, and so is h. Both of them are discrete sequences. This is an operation between two sequences to result in an output sequence, and we know the name of the operation is called convolution. So, we say x convolved with h gives you y. Convolution is an operation between two sequences, it is not an operation between two numbers, it is an operation between two sequences. How do we effect convolution? Let us see. You see, let us first understand what we would be doing to each sequence when we want to convolve. Let us take the sequence x of, now let the sequences be indexed by k instead of n, right. And let us look at what is the meaning of h of n minus k for a fixed n. So, for a particular n, what is the interpretation of h of n minus k? So, first let us take h k minus n. So, for a fixed n, and k is the index here. So, what is h of k minus n? It is essentially the sequence hk shifted forward by n, is that right? Now, if you replace, in fact, similarly h of k plus n would be the sequence hk shifted backwards by n, is that right? Now, in this, if you replace k by minus k, what are you doing? You are reflecting the sequence about k equal to 0, right. So, you are reflecting the sequence about k equal to 0. So, how do you get h of n minus k from h of k? You get it by first shifting backwards by n and then reflecting around 0. So, what is going to happen? The 0th point, so you see hk, see the 0th point is going to come to n, and H1 would go behind. So, the sequence would be reflected, isn't it? It is going to be mirrored around 0, which means that all the points after 0 would come in sequence before n, and all the points before 0 would come after n in H of n minus k. Is that right? Having done this, you now think of a train and a platform. Now think of a train and a platform. So, we have the best way to explain convolution is the train platform analogy. So, xk is like passengers sitting, if you are doing xk hn minus k, then xk is like the passengers on a platform. And h of n minus k are like the passengers on the train. The train moves, as n changes, the train moves, okay. And at every point what happens? Every corresponding passenger inside the train shakes hands with the corresponding passenger on the platform. The shaking of hands can be thought of as a multiplication of xk and h of n minus k at that particular value of k. And the combined effect of all this handshake is the output that you get at that particular n. And how do you combine? By adding. So, it is convenient and smooth and slick to explain convolution by using the train platform analogy. Is that right? Now, how do you generalize this to continuous systems? So, now you think of here, see, you can first visualize what is happening. When you change n, you first reflected h like this, isn't it? You reflected h in this manner, and then as you change n, you visualize that the engine is here. Of course, here you have to think of bogies being on both sides of the engine. Some trains have that, right? So, as the engine moves, it pushes all the bogies along with it in the same sequence. And at every point, there is this handshake, and the net effect of the handshake is the output at every point. Is that right? So, that is a simple way to explain convolution. Now, you see, how do you generalize this to continuous time? That means, if you have a continuous time system, how do you generalize these ideas? Well, that is very easy. You first notice that instead of summation, what should you do when you go to continuous time? You need to do integration, right? And of course, here you no longer have a discrete variable k, you have a continuous variable, you can call it lambda, right? And you are not calculating for every discrete index k, but you are calculating for a continuous index t, right? So, you have y of t for continuous time systems. You have y of t is integrated over all lambda, x of lambda, h of t minus lambda, d lambda. This is the operation of convolution in continuous time. And the same principle holds, except now it is more difficult to visualize this train platform, because you have a continuum. If at all, you may wish to think of it as, see, instead now you can't think of them as passengers, because they are not discrete anymore. But you can think of a continuous, say, a continuous structure on the platform, a static structure on the platform, which interacts with a structure inside the train which moves. And of course, it has a connection, right? So, you can visualize the static structure on the platform rubbing against a structure put on the train which moves, and the combined effect of the rub at every point in time is the output at that time, right? So, you can think of it that way. Now, of course, one can prove this, the proof of this can be done in the manner similar to the discrete case by essentially seeing what happens to one impulse and then expressing an input in terms of the impulse function, and then of course using the properties as we saw yesterday of shift invariance followed by additivity and homogeneity followed by additivity to establish the input output relationship. Okay. Anyway, the point is that this operation of convolution is fundamental to dealing with linear shift invariant systems. Now, convolution, as the name, in fact, the word convolve is the verb form of convolution, and convolve literally means to twist and mix in some sense. You see, when you talk about a convoluted argument, when you say some argument is very convoluted, what are you really saying? You are saying that argument is difficult to understand, right? It's a difficult argument to appreciate and understand. That's what convoluted means, right? So, convolution is inherently a difficult operation. In fact, a lot of students find the operation quite hard to understand initially. In fact, even as faculty, it takes us some time to appreciate and to convey this operation to a class, isn't it? So, naturally, one wonders what the implications of convolution are when you think of a signal as a combination of sinusoids, right? Suppose you were to apply a single sinusoid to a linear shift invariant system. What would it result in, right? Given the impulse response. Now go a step further. Think of a sinusoid as a combination of rotating complex numbers. Let's appreciate this. So, let's begin. So, this is the complex plane. You have two oppositely rotating complex numbers. They begin with a starting angle of phi 1 and an amplitude of A naught or A1. And this one rotates counterclockwise and this one rotates clockwise. So, how do we express these complex numbers? We know how to express the complex numbers. Each of them can be expressed in polar form. They rotate with an angular velocity of omega naught. Right? See? So, how do you express this complex number? It would be A naught, A1, I'm sorry. Now, when you write it in polar form, the angle is captured by e raised to the power j, etc., isn't it? So, A1 e raised to the power j omega naught t plus phi 1. And this one is captured by A1 e raised to the power negative of the same. What do you get when you add them? You get a sinusoid. Well, it gives you twice A1 cos omega naught t plus phi 1. So, you can intimately connect sinusoids to rotating complex numbers. Is that right? There is an equivalence. Where you have a sinusoid, you have two rotating complex numbers. If you have a rotating complex number, you can pair it with one more rotating complex number and create a sinusoid. In that sense, there is an intimate connection. Now, let us apply this rotating complex number to a linear shift invariant system. So, you have a linear shift invariant system. And it has an impulse response of ht. Okay. Apply to it the input A1 e raised to the power j omega naught t plus phi 1. Okay. And look at the output. Let's find out the output. In fact, I would request all of you to calculate the output, but here what we'll do is we'll write the output a little differently. Before we calculate the output, let's first establish a property of convolution. So, you see, we wrote the input-output relationship in a linear shift invariant system like this. Let's establish a basic property of convolution which allows you to commute the two functions involved, right. So, let us replace t minus lambda by another variable, let us call it alpha. And when lambda runs from minus to plus infinity, alpha will also run from minus to plus infinity. Is that right? So, when for a given t, when lambda runs from minus to plus infinity, alpha also changes from minus to plus. In fact, it changes from plus to minus infinity. That does not matter. So, one can rewrite this as, well, you have x of, so lambda is t minus alpha and h alpha. And of course, alpha would be going from plus to minus infinity, but you have a minus d alpha there. So, minus and this can be combined and you get minus to plus infinity d alpha. Is that right? And therefore, you can see that convolution is commutative in the arguments. So, convolution is commutative. Okay. Let's apply, let's find out what the output there is. What would the output be? Now, use this property of convolution. It's convenient here to write h alpha, h of x of t minus alpha instead of the other way. And therefore, you have the output being integral minus to plus infinity h alpha. Now, here x is this. So, a1 e raised to the power j omega naught t minus alpha plus phi 1, right, and d alpha. So, we have, now this can be split. So, we can split that exponential. E raised to the power alpha plus beta is e raised to the power alpha and p raised to the power beta. We can split the exponential. And we get, see, that's the beauty. We get the input coming out of the integral. That's what is noteworthy here. That's why the complex exponential is so attractive. The complex exponential comes out of the integral. And this is an integral which may or may not converge. It's an infinite integral, so we are not guaranteed. In fact, in general, convolution is an infinite integral. So, the convolutive integral may or may not converge, which means that when you give an input to a linear shift invariant system, you are not guaranteed the output is finite everywhere. So, in fact, that's what stability refers to, isn't it? A system could be linear in shift invariant, but it may not be stable, may not be Bebo stable, but bounded input, bounded output stable, which means you could give it a bounded input, but the fact that you are convolving the input with the impulse response can result in an output which becomes unbounded in some places or in all places. Is that right? Yes. Oh, sorry, yes. You are absolutely correct. I am so glad that you noticed the mistake. it's good to make mistakes once in a while, no? When writing on the board. It also checks whether the class is alert or not. Yeah. So, here, if you look at this integral is dependent only, an integral dependent only on omega naught, the angular frequency, right? Now, let us also interpret this integral in a slightly different way. And for that interpretation, we'll go back to our geometry, high school geometry. You see, in high school geometry, we learnt vector geometry. So now visualize a vector being written as a combination of components, orthogonal components, right? So let's assume that you're writing a two-dimensional vector. How do you write a two-dimensional vector? Suppose you have two two-dimensional vectors, let's call them V1 and V2. They will be specified in terms of their components, isn't it? In fact, now you can think of an n-dimensional vector, although you may not be able to visualize vectors beyond 3 dimensions, still you can conceive of them. You can always assume that whatever you're doing in 2 or 3 dimensions carries as is to a larger number of dimensions. So, a 3-dimensional vector would be similarly written. Then you can think of 4-dimensional, n-dimensional, where n is finite. And slowly you can start thinking of the dimension itself becoming infinite. And then a sequence is a vector. A discrete signal is a vector. Because you can think of each sample of the sequence as giving you the components of the vector. Is that right? Now, suppose you wanted to take the dot product of 2 vectors. What would you do? How would you calculate the dot product of these 2 vectors? You would multiply the corresponding components, isn't it? So, what is the dot product of these 2 vectors? V11, V21 plus V12, V22. Is that right? And this essentially means component-wise multiplication. Further, this is easy to generalize, right? Whether it's in 3 dimensions, you do the same thing component-wise. If it's n dimensions, you do the same thing component-wise. In fact, now as you take the number of dimensions to infinity, you do the same thing component-wise. And now you can take it also to the continuous dimension. So now, for discrete systems, we can start thinking of the vectors as we know them, start with 2-dimensional vectors, 3-dimensional vectors, n-dimensional vectors, countably infinite dimensional vectors, and then we make the number of dimensions uncountably infinite, which means you go to the continuous variable, right? Now, the continuous variable alpha there, for example, can also be thought as an indexing for the components. So, you can think of continuous functions also as vectors where the components of the vector are really the values of the function at every point. So, here for example, you can think of 2 functions, the function ht or h alpha if you like. So, continuous, the story we are writing down is continuous time functions, continuous time or continuous variables. Functions are also vectors. So, h alpha is a vector. Alpha is a component index. And at that particular value, h alpha at particular alpha is the component. Do we see this? So, h alpha is a vector. Alpha is the index. Like for example, here, what are the indices? The indices are 1 and 2, isn't it? component number 1, component number 2. So, there is a component number alpha, but alpha is a continuous variable. And similarly, e raised to the power j omega naught alpha is also a vector. And what is this vector? This is a complex coordinated vector. So, it's see now here we have to also now go one step higher than what we learnt in high school. In high school our components were all real, but now we have to accept complex coordinates also, right. So, here of course, by the way, h of alpha, though we are tempted to think of it as a real function of alpha because we encounter only real functions most of the time, in principle it can also be a complex function of alpha. Nothing stops, in signal and system theory, nothing stops it from being a complex function of alpha. Anyway, e raised to the power j omega naught alpha for a particular angular frequency omega is definitely a complex function, right. Now, this is also a vector, right, and again it is indexed by alpha and it has a component equal to e raised to the power j omega naught alpha at a particular value of alpha. Now, let us extend the idea of a dot product. You should be taking a dot product like this. You will be multiplying the components. See now, since you are dealing with continuous components, you would multiply them component wise, but then instead of adding, you will need to integrate. Is that right? Because you are moving from continuous, from a discrete set of components to a continuous set of components. Instead of adding, we will now need to integrate. Is that right? So, h of alpha, so let us take a minute. E raised to the power j omega naught alpha, and you would be integrating d alpha over all alpha. So, we would think maybe this is the dot product. Is this a dot product? Let us see. Let us see, is it a dot product? Well, to answer that question, let us take any two functions x1 and x2, continuous functions of t or continuous functions of alpha, right. So, you have x1 and 2 which are both continuous functions of alpha, they are functions of continuous alpha. Alpha is real. Now, suppose we define the dot product like this. Is this in line with what we understand from a dot product? Let us ask some questions. So, what properties do you want a dot product to have? Of course, a dot product should operate as it does in 2 dimensions with a linear combination, right. So, if I take a linear combination of vectors here, the dot product should also be linearly combined, right, which means, if I have something like C1 x1 plus C3 x3, right, and take a dot product with x2, it should give me C1 x1 dot x2 plus C3 x3 dot x2. We know this is the linear combination property of the dot product, which we should be, this of course carries all here, there is no problem. But there is another very important property of the dot product which we want to preserve. Namely, if I took the dot product of a function with itself, if I took a dot product of vector with itself, what should I get? If I take x dot x, what should I get? What should I get if I take the dot product of vector with itself? The square of the magnitude of x, mod x squared, the norm of x squared. Is that right? Now, if you want that to happen, let us see if it is going to happen here. Suppose x is complex here. So, if I use this definition of the dot product, what would happen? x1 dot x1 would be x1 alpha squared d alpha. But x1 alpha squared d alpha has the integrand here is complex. When a complex integrand is integrated, it is not necessary it will give you even a positive number. You see, the magnitude squared must be a non-negative number. It cannot be complex. So, x1 squared alpha integrated over all alpha is not necessarily, forget about positive, you are not even guaranteed it is real. In fact, it may vary. The other problem is this. Suppose you have a non-zero vector x. If I take the dot product of a non-zero vector with itself, can it ever give me 0? It should not. The dot product of a non-zero vector with itself should not become 0. But here it is possible, because if x1 alpha is complex, then x1 squared alpha integrated over alpha might very well integrate to 0. For example, if x1 alpha squared is essentially a rotating complex number, and if it completes several cycles, if it rotates only over one cycle, then it would integrate to 0, right. So, therefore, this definition is unacceptable. So, we need to change the definition a little bit. What change shall we introduce? A very simple change. We will simply complex conjugate this argument. The second argument would be complex conjugated. Now, let us see if our requirements are met. When I do this, what is the dot product of x1 with itself? It would give me mod, because x1 alpha complex conjugate is mod x1 alpha squared. So, now when I integrate mod x1 alpha squared with itself, it indeed would give me a non-negative number if x1 is non-zero. So, not only is the number non-negative, it cannot be 0 if the function is non-zero. Is that right? So, this is a little change I need to make in my definition of a dot product when I am dealing with complex coordinates, right. So, now we have a beautiful interpretation for this. Now, the first thing is this dot product needs to be changed, isn't it? So, if I want to take the dot product of the impulse response with e raised to the power j omega naught alpha, I need to complex conjugate this argument. And therefore, I have this quantity h alpha e raised to the power minus j omega naught alpha d alpha over all alpha is essentially the dot product of the impulse response with e raised to the power j omega naught alpha. Now, this has a beautiful physical interpretation. You see, go back to your high school physics again. Suppose you wanted to analyze the effect of several different forces upon a particular system. What would you do? And you know the system behaves in a certain way when a force is applied in the horizontal direction, and you know that the system behaves in a certain way when the force is applied in the vertical direction, right. So, you know the system behavior when the force is applied in one direction, you know the system behavior, and you know the system is linear. That means you can apply the principle of superposition. What is the principle of superposition? You can find out the effect of each of the forces independently, individually, and then combine them in the same way to get the overall effect, right. So, if the principle of superposition holds, and if you know the behavior of the system when a force is applied in two perpendicular directions, what would you do when you have a system of forces applied to the system? You would first decompose each of the forces into their components along these two orthogonal directions, and you would take the sum of components in each direction and find out the net resultant, isn't it? Now, what are we doing here? The impulse response is like the response of the system to a particular kind of input, e raised to the rotating complex number rotating with an angular velocity of omega naught, right. Now, what is this impulse response doing? The impulse response takes this as the input and produces an output which is of the same nature. And in fact, the impulse response, when it acts upon the rotating complex number, simply multiplies the rotating complex number by a constant. That constant is this dot product. So, it is as if this linear shift invariant system thinks of e raised to the power j omega naught alpha as a special kind of input to which it seems only needs to multiply by a constant. What is that constant? That constant is the projection of the impulse response upon that rotating complex. So, you can think of this in terms of your high school understanding of forces and the action of forces, right. The impulse response acts upon a complex exponential only to multiply the complex exponential by a constant, and that constant also has a very simple interpretation. That constant is the dot product of the impulse response with that rotating complex. So, it all fits very nicely, and that is the reason why we like to think of the signals that we apply in terms of these rotating complex numbers of different angular frequencies. And we know what happens to each of the angular frequencies. So, we can now combine the effect of each angular frequency and get the overall output. Is that right? So, we shall meet again at 11 o'clock